Hello, ladies and gentlemen. I hope you're all doing well and you're ready for question number 8 on our 2012 Euclid paper. All right, so we've got two written parts here, A and B. What have we got? On Saturday, Jimmy started painting his toy helicopter between 9 a.m. and 10 a.m. When he finished between 10 a.m. and 11 a.m., so it took him maybe at most 2 hours if he started at 9 and ended at 11. But so he finished between 10 a.m. and 11 a.m. the same morning. When he did that, the hour hand was exactly where the hand had been where he started, and the minute hand was exactly where the hour hand had been when he started. Jimmy spent T hours painting, determine the value of T. So here's sort of their example without sort of specifically committing to numbers, but the hour hand between 9 and 10 is now where the minute hand is now where that is. So the minute hand is between 9 and 10. So we can see he finished sometime between 45 and 50. He started between 9:50 and 9:55. Okay, but it's not enough to estimate. We need to actually figure out how many T hours he worked. All right. So how do we approach a question like this? Well, you can actually tell the time on a clock like this, knowing exactly where the minute hand is or exactly where the hour hand is, because as the minute hand moves, the hour hand moves, and the minute hand's sort of always moving, and it sweeps out angles. Now we've got 12 numbers around the circle. 360 divided by 12 is going to be 30 degrees, so I think that will help. But how best to approach this? Well, we need to figure out, do we necessarily need to figure out the start time and the end time? That's a good question. Um, it should be determined purely by the hour hands. So we might say something like 12, 11, 10, 9. So the hour hand was here. And then at the end, 12, 11, 10, 9. The hour hand is pointing about here-ish. But you can tell the time purely from where the hour hand is. All right, now, I know between 9 and 10 it's 30 degrees. Okay? And we could comment like, 360 divided by 12 hours, 30 degrees per hour. Because this is a written question, we do need to actually say what we're doing. So one thing we might choose to do is maybe say, all right, suppose the clock started T degrees above the 9. Because the 9 sticks out nice and horizontal. So, well, actually, no, T is in the question, isn't it? So let's say X. Okay, so we start X degrees above the 9. Right, and then we end with our hour hand maybe Y degrees above, but Y is going to have to be between 30 and 60. X has to be between a 0 and 30. Now, the way the question's phrased makes me think that there's only sort of a unique pair of minute hour hands that will do this. So there's got to be sort of a unique answer. I would suspect, at least. Um, hmm. Well, so we could say something like the hour hand moves 30 degrees per hour, and so it moves 30 degrees in 60 minutes, so it moves half a degree per minute, whereas the minute hand moves, well, a full 6 degrees per minute. Okay. So wherever the minute hand is at y, which I guess measuring from the total is 270 plus y. So the minute hand. Let's say the hour hand starts at 360 plus x degrees from 12 clockwise, and the minute hand starts at 270 degrees plus y degrees from 12. And I don't need to say clockwise again. They're gonna realize I'm meaning clockwise. Okay, but these two things would have to be linked. If you know your x degrees from the nearest hour, x degrees divided by a half degrees equals a number of minutes past 9, whereas 270 plus y degrees over 6 degrees is the number of minutes past 9. So this should give me a nice little relationship. X divided by 1/2 is 270 plus y over 6. Now we could multiply both sides by, well, we could say 6x is the same as 1/2 270 plus y. Sort of cross multiplying, bring the 6 over, bring the half over. Multiplying by 2 again, we get 12x is 270 plus y. So that is, I suppose, a nice relationship. Okay? I don't want to assume that there necessarily has to be a sort of an integer number of minutes or anything like that. It may come to that, but I don't think we should assume that. So I can't just say, oh well, look for a multiple of 270, a multiple of 12 past 270. I don't think that's the best way to do it. Okay, but then we also have a similar relationship because the hands switch positions after the hours. The hands swap, and so now 300 should be, so this is 270, so to go another 30 to 10 should be 300. And so y minus 30 is sort of the hour hand moving past 10. So that gives me the number of degrees that the hour hand is past 10. And so y minus 30 degrees over half should be the same as, now it's 270 plus x degrees over 6. Right? And that should give me another relationship because these are both the number of minutes past 10. All right, so multiply by 6 over here, so 6y minus 180 is 1/2 270 plus x. Multiplied by 2, so 12y minus 360 is 270 plus x. And now we could say something like 12y is an add-on. It'll be 30, so it'll be 630. That's 9 times 3, that's 9 times 4, so 9 times 7 plus x. And there we go. So what have we got? We've got 12y is 630 plus x, and we have 12x is 270 plus y. Okay? This is great. 2 equations, 2 unknowns. Let's rearrange this one here and say y is 12x minus 270. And then this should give us x. All right, so we get 144x minus, let's grab my calculator to make this go a little faster. 12 times 270 minus 3240 equals 630 plus x, so 143x should be 3870. And does that actually, it's not a multiple of 143. Well, that's okay. Do they have anything in common? Yeah, it looks like, well, 143, no, 3870 divided by 13. Nope. Divided by 11. No. Okay, they have nothing in common. But there's x, and now I can figure out y. And then we might be able to then say, all right, well, how many hours have passed? And I guess all we really need to do is work out the difference in the number of minutes. So this is the number of minutes past 10. This is the number of minutes past 9. So how many more minutes to get to 10 and then go past 9? That would certainly be sort of perfectly acceptable way to approach it. I was hoping it would divide out. Clearly it didn't, so that's okay. So what was it? The number of minutes past 9 is x over a half. And then the number of minutes past 10 is 270 plus x over 6. Okay. So this number plus 60 minus this number should give me the number of minutes. I'm going to stop writing x over half and just write 2x. Okay. So that would be the number of minutes in the time it took to paint. Who was painting? It was Jimmy? Yeah, Jimmy. But if I want the number of hours, divide by 60. I'm going to put everything over 6. I'll get 2, so I'll get 630 minus 11x all over 6. And then we want to divide by 60. 630 minus 11x over 360 equals the number of hours. So that's t. Okay. 630 minus 11x over 360, that's t. But we did work out what x is. It was that really big number, 3870 over 143. There, at least some 11 here and 11 down here will cancel out with a 13. All right, so 630, just cleaning up the fractions here. 8190 all over 13 minus 3870 all over 360. So 8190 minus 3870. And we get 4320 all over 13 times 360. Can I clean any of that up? Oh, 4320 is just 12 times 360, so we get 12 over 13, and that should be the value of t. So 12/13ths of an hour. There we go. I didn't think it would clean up that nicely just because the numbers were quite big and ridiculous, but there we go. Not too bad a question. And we did manage to show our work. We got pictures showing our setup and everything. We've described our angles. You'd probably write a bit more of a sentence for what you're doing, but we explained exactly how we're getting our calculation for t there. So there we go. Good answer. And now we got B. Determine all real values of x so that, so we got some logarithms. Now, my usual advice when it comes to logarithms or function questions that appear in 7, 8, or 9 is that they are actually a lot more doable than you think. They tend to be sort of scary, especially logarithms. I find people are a little intimidated by logarithms just because it's something you learn so late. But as long as you're comfortable with the basic logarithm rules, which are things you should definitely review before attempting the later questions on the Euclid, in case this pops up. But if you're comfortable with those rules, these questions aren't ever particularly bad. Now, when I say rules of logarithms, I mean things like log a of y plus log a of z. If you've got the same base here, you can, I guess should be a y and a z, you can multiply things on the inside, these basic rules. Now, I mentioned that because I'm noticing I have different bases here. It's kind of interesting. Something else that's catching my eye as I do this, x plus 3. Well, this expression in here is x plus 3 squared. So let's see what we can do. Copy these down. It was 5x plus 9, x squared plus 6x plus 9. There's something in there, and I think it was equal to 4. 5x squared plus 24x plus 27. Is that going to be the square? No, it can't be the square of that. There's a 5x squared, not a 25x. But that 5x squared up front and the 27 is a multiple of 9. I have a feeling there's a little bit of work we can do there. First things first, let's write this as x plus 3 squared. And then log x plus 3 here. Now, if this were 5x plus 9 times something, which I'm really hoping it is, we would need just an x and a 3. Well, that makes me feel even more correct. 9 and x is 9x. 3 and 5, 15. 15x plus 9x is 24x. So yes, this does work. Great. Okay, so what can we do? Well, we can actually reverse the rule I just told you a moment ago to break this up a little bit. You can also bring the 2 out. Log rules say that exponents inside a logarithm can turn into coefficients outside. And there's another nice log rule that says if your number inside matches your base, it's just 1. Now we still have 2 logarithms here with different bases. So what are we to do with them? Well, you'll notice we have an x plus 3 inside and x plus 3 out. An x plus 3 outside and x plus 3 inside. It's a rarely used rule. It's based off of the change of base formula. But log of b base a is the same as 1 over log of a base b. So what I'm going to do is we've already used x, so let's say let y equal, we'll do the 5x plus 9 one. Okay. So if this is y, this is 1 over y, and what we've reduced this to is just going to be a quadratic. So we get 2y plus 1 over y is equal to 3, because the 4 on the one side and the 1 on the other cancel it out a little bit. Okay. Well, now let's just treat this like a regular quadratic. Multiply by y on both sides. This is not going to be too much of a problem. Y can't be 0 at all, so we haven't really lost anything. And then we could quadratic formula this, or 2y and a y, and I need two things that multiply to positive 1, but I need some negative numbers in here. Let's try negative 1, negative 1. Negative 2, and then another negative 1. Yeah, that gets negative 3. There we go. So either y equals 1 or y equals a half, which is great. Except they didn't ask me for y, they asked me for x. But now I can take each of these and do something with it. So, for example, if this is y and we take y as 1, any logarithm statement, so, log b base a equals c, can always be rewritten as a to the c equals b. Logarithms ask, what thing do I have to raise a to the power of to get b back out? So if you have a nice complete equation like this, you can always rearrange it to something you're a bit more comfortable with. You're likely to be more comfortable with exponential statements. So then 5x plus 9 to the 1 is x plus 3, which is just 5x plus 9 equals x plus 3. So 4x equals 3 minus 9, which is negative 6. So x is negative 3 halves. Now, real quickly, we should double check because you can't have as a base for your logarithm a negative number. So just quickly off to the side, you might want to double check. Can I use this number in my base? So that'd be negative 15 over 2 plus 18 over 2. That'd be 3 over 2. And, of course, the other possible base is this x plus 3. We don't want it to be negative. Well, negative 3 halves plus 3 is 3 over 2. And now you'll notice, hey, both of those expressions are equal. Well, that's what we just solved for. Okay, but this works. This is an x value, because they did ask for real values of x. Okay? Real values of x, so negative ones are perfectly fine as long as the logarithm statements are satisfied. If it had worked out that 5x plus 9 with this particular x was negative 2 or something, we would have had to ignore that. Okay? You can't do something like that. You can't have a negative number in a logarithmic base. Okay? You can't plug a negative number into a logarithm either. You got to watch out for that for some of these find all x's that make these logarithm statement questions true, because that's a quick catch at the end, and sometimes it eliminates some of your answers. All right, so that's the only possibility if y equals 1. What if y equals 1 half? Okay, so if this is 1 half, again, we can quickly rearrange this into a nice little statement like this. Okay, now what do we do? Well, we could square both sides. That gets rid of the 1 half. Because 1 half, if you got a 1 half and a 2, exponents in the top multiply together, and 2 times a half is just 1. All right, and this gives me a nice little quadratic, one that we actually saw earlier in the question. The 9s will cancel out, and you'll be left with, you bring the 5x over to the other side, x squared plus x. So that's x times x plus 1. So in theory, x equals 0 or x equals minus 1 should also do the trick. But again, we should double check. Do I get any, is 5x plus 9 or is x plus 3 going to be 0, or not 0, well, 0 or negative aren't allowed. Okay? And we quickly check. 5 times 0 plus 9 is just 9. And 0 plus 3 is just 3. And yeah, hey, 9 to the 1 half is equal to 3. What about -1? Well, -5 plus 9 is 4. -1 plus 3 is 2. That also has this nice square root relationship. 4 to the 1/2 is 2. So we're not only double checking our arithmetic, but we're also making sure that we actually get bases that are allowed. Okay? But that's it. These were the two cases for y equals 1, y equals 1/2. We've explored both of them quite nicely. And so we can say the only real values of x, in fact, these are the only values, period, were 0, -1, and -3. Or sorry, -3 halves. And that's it. We don't really have anything else to say. We don't have another part to the question. We have double checked, as you always should with logarithms, that the things you're inputting aren't negative or 0, and the bases aren't 0 or negative either. Okay? And if you wanted to, you could grab your calculator and double check that everything adds up to 4. But I'm really confident in our work. It was nice. It was clean. It wasn't bad. It's just sometimes people don't know their logarithm rules. Sometimes people are just intimidated by logarithms, and I would encourage you not to be that sort of person. And if you are scared of a question like this, get to know logarithms. They're actually a very useful tool. And if they're not something you're encountering a lot in high school, I assure you, when you move on to, say, university calculus, you'll see a fair number of logarithms. Okay? But that's it. I'll leave you to look at logarithms on your own. We're going to move on to question number 9, and we'll take a look at that next time.